Okay. Oh, sorry about that. The goal of today is to have you get to work. So I've tried to organize it indeed in the way that I'll give a short introduction, and then an assignment, and then again an introduction, and then an assignment, and again until until either we run out of motivation or the time is up or whatever. So let's let's go. So what we were in a block, which was a little bit block P, so, calculating the optical properties of blood. This falls in this theme because the main scatter in blood is of course red blood cells. So if we can model red blood cells as particles, as scattering, discrete scattering particles, then we can perhaps model scattering by blood as scattering by a discrete random medium. Discrete means the particles, there are discrete particles which have random positions inside. We briefly encountered this already in the first few lectures. The main tools that we found that we're using that with the pair correlation function, the sample structure factor that actually describes how the scattering is follows from this. So just for completeness, the level that we are describing will essentially be this because we will use concentrating on the scattering properties of a single particle so much today, but more like how the ensemble of particles will interact with that to calculate propagation through such an ensemble. Briefly, these were the optical properties we have for single particles, for absorption and for scattering. The efficiency was a dimensionless quantity that described the ratios of absorbed power and incident power and scattered power of incident. From that, we could calculate geometrical cross-section by multiplying this efficiency with the geometrical cross-section. We would get the absorption cross-section, or scattering cross-section. Then we get the ratio of absorbed power of incident intensity. Going to multiple particles, then the formal way of approaching that would be to define the absorption cross-section as coefficient of the scattering coefficient, total cross-section per unit volume, so adding all the cross-sections and dividing by volume, and if particles are identical, simplify. This equation is low, so the number density of particles per unit volume. But of course, there was a caveat in that the organization of the samples mattered. If we did this thought experiment where we put all the absorbing molecules to one side of the pipette, we got different absorption coefficients than when all the molecules were homogeneously distributed. That was also the case when the absorbing molecules were taking particles with different absorption coefficients, suspension compared to the solution, even though they both contained the same amount of absorbing molecules. And this organizational, this method of organization also expressing scattering, dilute sample scattering scales, scattering coefficient scales linearly with density. If the medium is dense, particles are not far away from each other, very close, and we had to include this correction factor that included the bigger picture of the optical properties. I will be focusing, of course, on this part here today. So for scattering, it's important to consider the relative positions of the scattering particles, and an extreme example of that is, of course, a crystal, where the scattering centers are neatly arranged in the grids. You can use light to probe actually the structure of this crystal by looking at these patterns. very specific angles, and depending separation between the scattering centers. The same holds true. The same effects hold true, but less predictable than positions. Randomized, the procedure is the same with calculate scattered fields in all the scattering centers and then add calculate scattering density and scattering density. The cross section and the coefficient. Okay, the step to tissue modeling is a little bit on top, of course, because what we're going to be assuming in this case is if you want to measure a model tissue in such a way, then we assume or we rationalize it by saying, okay, suppose tissue has a dominant scatterer, that can be the nucleus, it's a large scatterer, mitochondria, so it's smaller. Then we're going to suppose that the scattering of one nucleus is like a scattering of one particle. That way we can that way we justify using this kind of theory. Of course, in practice, that is, or in reality, that is not a huge approximation because the biological markup of the tissue is much more complicated. So, as a brief as a brief spoiler, there is another theory that we can use to describe more complicated tissue that is called continuous random mediums instead of discrete scattering centers. We assume that the medium is consistent of a continuous fluctuation of refractive index, and you can scattering from that. We'll look into that into the next for the next classes. But for a medium such as blood, which really has well-defined cells, and the internal structure of red blood cells is also very simple because it's empty. It's just a sac of hemoglobin. So there, the justification is a little bit more in place, I would say.
Even kijken wat er in de chat staat. Waarschijnlijk dat hij me niet kan horen. De microfoon hier. Is dat hard? Okay, I'll try to speak up and speak slow.
We looked at this example to see why the organization mattered. The lecture hall or the concert hall where people were allowed to pick a chair in a row before they entered, and then of course the problem could arise that some people picked the same row and the same chair number, so you would end up with more than one person sitting in one chair. But the statistics of this problem is fun because you can calculate what the average number of people per row is going to be. We'll follow a Poisson distribution. In the Poisson distribution, we have calculated here. For this Poisson distribution, you can also calculate the variance, the fluctuation of the number of people per row, and that is the same. It's the same as the mean number. So if you keep adding people into the room, then the mean and the variance will change at the same rate. So the graph now, of course, if we have restricted seating, so to say, one person allowed per room, then we need a different statistical distribution to describe this effect. That can be found by first calculating the probability of having a number of chairs per row occupied and a number n minus k per row unoccupied. So that's given by that expression, and then taking into account all the number of ways that this can happen with a binomial distribution. So a binomial distribution for the number of filled chairs in a row that has 10 chairs. Binomial distribution. And again, from that distribution, we can calculate an average that is the same as for the Poisson case. but the variance for the binomial distribution is different. And mainly it scales as a linear term with the density, but also a quadratic term. Means that if we, what happens, of course, that if we keep adding people to the room, the mean number of people will increase. The variance, the fluctuation of the number of people will dampen out, because in the end you will have one person per chair for all the rows, so zero variance. So graphically, that's kind of happens. Mean just linear up and variance. Yeah, the same thing. The same thing happens with particles in the medium. So just like the restricted case for the shares of particles in the medium may not be completely randomly distributed. They cannot just take every point in space. Because they can at best can touch, but they cannot overlap in space. So that means that the phase differences that are from the light that is scattered from these individual particles is not totally random. So we can have finite certain structure in phase differences of the light that hits the detector, which means that we can have interferences, either constructive or destructive. That will in the end enter into the scattering coefficient, as we will see. All right, that was the question. So if we take a medium consisting of hard spherical particles, discrete random medium, we can look at this situation. We take a reference particle somewhere in the center of that medium, and we're going to count particles we encounter in the spherical shell radius r at some point away from that. This function, so we can make a histogram of the number of particles we encounter, and if we normalize that on the number of particles that we would encounter if there were no constraints, so when all the particles were allowed to take any position, then we get the value for the so-called pair correlation. Kijken wat er in het volgende item is. Ah ja, dat was de pair correlation function. So what happens in terms of light scattering? We have all these particles in the medium. They will all scatter. They will all give the scattering field that is proportional to the incident field, proportional to the spherical outgoing wave. This amplitude function S that describes how the light is scattered into the different directions. And there's a phase term that depends on the position of the particle. Now, if you now take two particles in such a medium, and if you assume that it is both homogeneous and isotropic, so homogeneous means that the statistics are the same anywhere you are in the medium, and isotropic means that it does not matter from which side you look at this medium; it's always going to see the same thing. Then the individual positions of the particles are not relevant anymore, because only the distances. Put in other words, there is no obvious particle that serves as a reference particle. You could pick any other particle and call the same distance. So the only thing that we're then interested in, or the only thing that will report is the distance between these particles. That is where this pair correlation function comes in as a histogram of the distances between particles. Okay, so I want to borrow a little bit from statistical mechanics to see how this pair correlation function arises and what's actually the implication of the scattering. So let's start with the volume V, a system of volume V, which has capital N particles in there. We're going to define the probability density function of particle coordinates P of N. It's a joint probability density function. In this notation, and what this tells us is that So R is the position of the particle, Bayesian from the coordinates method. This will have, if we have n particles, it will have units per volume, it's probability instance. It will have units probability per unit volume raised to the power n.
Because it's a joint probability.
And if you multiply probability exponential with DR1, DR2, etc., what you then would calculate is the probability of simultaneously finding particle 1 at volume DR1, which is located at R1, and particle 2 in volume DR2 located at R2, etc. Joint probabilities. Yep. And this, and since it is a probability density function, it is normalized. If you carry out the integrals over only space, then the answer should be 1. That is enough. Now from that you can calculate partial probability densities. What we do here is we have a joint probability of particle 1 to n. We're going to integrate out from n plus 1 to capital. That's integral dr plus 1 to dr of this field. So what that would yield is the probability is of simultaneously finding particle 1 at R1, particle 2 at R2. So the nth small n particle. Regardless of the position of all the other particles, because we integrated out the positions of particles. So we still have a probability density that relates to particle 1, particle 2, etc. The positions of all the other particles are now integrated out. So if you use this formulation, then all the particles, these particles 1 to a small n, are labeled. So we have designated really one particle in the volume as particle 1, and the other one is particle 2. And the positions are also assigned. This is really finding particle 1 at a volume at R1. It's probably a more interesting question. There is not usually the labels for the particles, but asking just the probability of finding a particle, just any of them at R1, and another one at R2, and yet another one at Rn, etc. Regardless of the position of the remaining ones. So basically, get rid of the particle labels. You can do that. There is this number. How to even say this? But this is the number of ways to arrange these n particles in n positions out of n particles. So you can, if we add all these possibilities together. We can find a new function, a distribution function, as a measure of this probability, and that is so we still here at partial probability function particles multiplied with number of ways in which we organize it. Then we get this new function rho of n. So n particles, the other ones. Can take any position out of any total. It's a measure of probability, or it's a likelihood, because now this way, this rho is not a normalized function. This was normalized. We added a preflector here, so it is no longer normalized. The measure of the probability is just a straightforward. Okay, so this is the intermediate result. So now let's see what happens if we consider this for a specific number of particles. So let's say for n is 1, one particle, then the expression reduces to expression here, and we can integrate this over R1. Essentially, this reduces to n, of course. Faculty divided by n minus 1 faculty reduces to n. And we can integrate this one over R1. That is the only coordinate remaining. We have already integrated all of the other ones before. So that is because function is normalized. This whole integral values to unity, and the answer in the end is n.
Yeah.
So that means that the row of n is the local density. So integrating over position is something that follows to you. So the reality is the density. And for this homogeneous and isotropic medium, that is just constant, so there will not be dependence on R, so we can just do this. And here it's per volume per unit. Okay, but in this two, we can do the same exercise. So this two here, we have units per volume squared. And as we argued before, for homogeneous isotropic medium, this can only depend on the distance between particles. Preferred point to serve as the origin. So what rho then means physically is the likelihood of finding a particle at R1 and another particle at R2 simultaneously, regarding of the positions of all the other particles. That is what we calculate. That scales, of course, with the density squared. Because the particle is also by means of this argument density likely depends on the particle separation. So we can use that knowledge to implicitly define so-called pair correlation functions. Like this function here is proportional to density squared. And the new function depends on the only particle separation. That one is called pair. That one is called pair correlation. Rayleigh distribution. So this way, it derives from the starting with probability density of all particle positions within the medium. So this goes down to the Rayleigh distribution functions. That one we can integrate too. We can integrate over R1 and over R2. Filling in the substituting from the previous slide, rho squared times those functions here are n times n minus 1. It depends only on the scale of R. The distance between the particles is this case not which is the scalar distance. So we can perform this integration here, which is 3D integration. We can form it in spherical coordinates. So instead of en quadratie bestaat uit tijd en v. Of course, there is no theta and phi dependence here, so the integration of these angles is just add 4 pi over here, and what is left, the integration is the cos squared. That is equal to n minus 1, because this n cancels with 1 times rho. Here we have rho squared phi, the rho times phi is also n. So that cancels out. So on this side. Okay. If we calculate rho times 4 pi r squared times gr, dr is the number of particles in a spherical shell of radius r and thickness dr. That at the distance from some arbitrary. Also, 4 times P times R squared R is the volume of that shell. So rho times G of R is the local density at the distance R away from reference point. We can say that at the distance R because the medium was homogeneous, so it does not matter where in the shell. And if you would end this integration, so this integration counts basically all these little shells together, so it counts all the particles, and it adds to n minus 1. It makes sense that it adds up to n minus 1 because we're now counting all the particles except the reference particle from which we so that is fine. N total number of particles. So we had fixed N and fixed volume now, so we can loosen this restriction and write what we had before. But now with no, so the density considering N particles, but not with a limited number of particles. So we write it as the sum of any N particles and capital N particles of N times a probability distribution for finding N particles. We're not going to find that any further. It's not necessary. We can write so this is the sum of some quantity over the probability distribution. So that means that we calculate an average. The average in this case of rho N. General forms. The average of some property A, average over all the particles. Again, taking into account that we can have any number N particles. Same interpretation, but now with N undefined. Okay, we can try to normalize this. So take this function and integrate it over all spatial coordinates. Substitute for rho of N here. The probability P. Making use of the previous result for rho, so we substitute this general expression. Technical terms in there. And then finally, this normalizes the unities, switch from integration and summation. The integration of this P is normalized so that it's the unity. So the end is after integration is this expression. And so again, that can be evaluated for different values of small n. So if n is 1, that means that it is just calculating the average number of particles. If n is 2, work out that the result is that we have the average of n squared minus the average of n. And the higher orders we are going to ignore. So this is the result repeated. Now we can combine these two expressions, and this is the final step in continuous manipulation. So we can subtract the expressions for things two. This result. And this makes sense to do that. This in a sense is a correlation function of densities. So the previous results make another substitution that in terms of rho squared CR. So we're going to fill that in. I'll write this down in a Word document so that you can follow it a little bit. The final result is interesting, but now we have this expression on the left hand side, so On the right hand side, we have the average squared minus the average squared, and that is the definition of variance. Getting back to the election. Variance is the number of particles in the volume. So if we integrate this Form 1 integration, this expression here, and then it yields effective means for you. So again, combining that with rho, this, so now we have n plus rho times this integral of square relation to the left hand side of the variance, and the right hand side. So finally, final result on this thing that divide anything by n, then the ratio of variance over the mean of each part is expressed here in terms of pair correlation. So if you take a volume with these marbles that cannot overlap in space, then for a given density or important fraction, like to calculate the ratio of the variance, mean the number of particles in sub-volumes of that larger and why is this important? Well, if we think of scattering by particles, we can think of scattering taking place at these particles. It means that the number of scattering events, the variance in the number of scattering events, should follow the same behavior, weighted of course by the scattering efficiency. But from this we can get a grip on multiple scattering processes in such a medium, because the mean number of scattering events and variance of the number of scattering events. We'll follow that behavior. Okay, so the pair correlation function made quite a few appearances already, but getting a closed form expression is a different exercise altogether, and that's way beyond what we're going to do here. So I'm going to kick that can down the road. I'm just going to show you something that is workable. The gas model. So for the gas model, we have a pair correlation function that looks like this. So 0 for distances between particles less than the diameter, and unity for distances larger than the particle diameter, basically. Well, these two, so if you have R over distance over diameter here, unit 1, then there is 0 probability of finding a next particle if the distance is less than the diameter, and if the distance gets at the diameter or larger, then there is constant probability of finding the second particle. So that is this works very well for dilute samples, low volume fractions. If the volume fractions gets a bit higher, then the probability of finding two particles close together increases. And one common model for that is the so-called packed sphere model. It looks almost the same. Instead of less than or equal here, diameter itself is taken out of the equation for the location of the diameter. You get a constant offset. So basically, that one looks like this: 0 probability when the diameter is when the distance is less than the diameter. Some increased probability with the magnitude, this magnitude at exactly the diameter, and then after that constant again for the larger separations. And then the final, more sophisticated pair correlation function that is often used is the so-called pair solution, analytical solution for a hard to prove. That I will show you in the next slide. So that is shown here. So in black, it's the same graph as this. In black, there is the low volume fraction solution for zero probability. The diameter of the separation is less than the diameter and constant. It's larger. For higher volume fractions, you get increased likelihood of finding another particle at multiples of the diameter. So that is what you do. And eventually, if the distance gets very, very large, then there's again some kind of constant probability. Yeah. Okay. Now again, so this how does this relate to the assumptions we had before? Well, to calculate for these pair correlation functions, we can calculate again the ratio of the variance, mean of the number of particles in the medium. And if you do this for that Perkins-Yavik pair correlation function, even though the expression for the pair correlation function itself is quite complicated. The end result of the integral is pretty straightforward. It's a function of volume fraction only, and its shape is something like this. So you have volume fraction here. You have this ratio of variance. Let's just plot the variance here. So in the graph there, this would be linear scaling, this would be quadratic scaling, and the result of pair correlation for the Perkins-Yavik is but the convenient result is that it is a function for the function. Okay, so now my question for you. So this was the result. I used that Perkins-Yavik function. This result is so for the blue and the red function. And the question is now, what if we use the gas model for pair correlation function? Can you now solve that integral and express this ratio as a function of volume fractions, just like on the. Then, if you get an answer, then can you check that by making a Taylor expansion of this function? So and for low volume fractions, you get the same result. Go ahead, use anything you like. Yep, sorry.